And I'm happy to go over any question from any homework that you might have had.
I have a question.
Yeah, go ahead.
So my question is from the Khan Academy, the final Khan Academy assignment, normal calculations in reverse.
Mm-hmm.
And I just didn't understand like the 20% of profit. So I was like, I got the question wrong, and I was like going over the hints that they show you.
Mm-hmm.
And I just don't understand how you find like the area of the curve that is 20%, because it seemed like when they went onto the Z table, they went to -8 and 0.5, and that was like not 20%. So I was just wondering like how
Okay.
they.
So I'm pulling it up here. Which one specifically? Do you remember if it was question 1, 2?
Yeah, question 1.
Question 1. Okay. So I'll just share my screen here. Google Chrome. So the distribution of annual profit at a chain of stores was approximately normal, with mean 66,000 and standard deviation 21,000. Okay, and I'll write some of this down in the notes as well, so I just have it so we can try it out. So this is just a little bit of homework review. The executive conducted an audit of the stores with the lowest 20% of profits. What is the closest maximum annual profit at a store where the executives conducted an audit? So on the notes here, which you can't see, I'm drawing a bell. I always like to sketch it out because it just kind of helps me visualize. So I'm drawing a bell shape. I know the middle of the bell shape, the bell curve, is 66,000. And the variance, or the standard deviation, sorry, is 21,000. So plus or minus 21,000 tells me kind of roughly the width. But I want to capture an area, and I'll show you guys this picture, later in a second. I want to capture an area that contains the bottom 20%. So if you can see in the camera, draw here. So this is what I'm looking for in the picture. So I'm looking for that. So anyone volunteer, like what we should look up here? How we should use the Z table? Oh, okay, yes, good. Some people said that they struggle with these, so I'm happy we're going over them. Yeah, so let's go to Z table. We go to Z table, ztable.com. And yeah, Gabby, what did you suggest? I like your idea. Let me just suggest it.
I said that like you go to like the decimals on the Z table and you basically look for the closest thing to 0.02 as possible, because that's where the 20% is going to be.
Yeah, a point 0.20.
Yeah.
So it's going to be somewhere around here. So now we're looking for these are the probabilities. These are the z-scores, right? And then the hundredths place of the z-scores up here. But the numbers in here are all the probabilities. So if we want to find the bottom 20%, just look up 0.20. Where is that? It looks like the closest one is, wait a second, what's going on here? 0.8. Why are these, oh, I see. Yeah, it's going, these are decimals these are becoming more negative here. So right here, I would say is probably the closest, no, actually this one is a little bit closer to 20%. So you could use this z-score, negative 0.8, what is that going to be? Negative 0.85 or negative 0.84. If we really want to guarantee that we get the bottom 20%, you probably want to use negative 0.84. So is that okay how why I picked this number as the percent? Okay, so that's a good question. Let's, Gabby asked, why would you use 0.9, the 19.77% versus 20.05%? I just thought of it because it's closer, in terms of the rounding. But if we look at the question carefully, maybe we're not supposed to use that one. Probably it's not going to matter much for like our answer. It's probably going to be the same answer regardless. But it says, what is closest with the lowest 20% of profits? So, maybe to make sure that we get 20%, maybe you'd pick the one a little bit above 20, just a little bit above 20%. So it doesn't matter. Like either one will be really close and give you the same answer, basically. So pick negative 0.84. Are there any questions how I get the z value of negative 0.84? Okay, so now let's plug it in. So now we're gonna, our goal, the z value tells you how many standard deviations you are from the center. So I'm gonna do 66,000. I want to use the equation x equals mu plus z sigma. And that's not really an equation you have to really think too much to memorize. It just means because as long as you understand that the z-score tells you how many standard deviations away you are from the average. So I'm going to write that x equals 66,000 plus negative 0.84 times what was 21,000. Okay, so I have it here. I don't know if you guys can see it. So just like that. And it's about, so 80% of 21,000 is about 16,000. So if you take away 16,000, yeah, it looks like it's going to be around about 48,000 will be roughly the profit there. But we can double check just to make sure. I'm just going to use my calculator here. 0.84 times 21,000 is 66,000. I got 48,360 when I did this. Any questions? Did that help a little bit? Any points of clarification, or do you guys want to go over try another one? By the way, can you see my my video? Okay, or is it small? Maybe it's small. Nice, Archer. Where did you go wrong? If you don't mind to share. Oh, I see. I see. Yeah, so normal in reverse is really nice and useful to know how to do. But basically the idea is, right, so you look, nice, so 20% means it's the probability of some part of the curve. So you look for that area inside of you look for the z-score corresponding to that number. So you're trying to find that number in your table, something the closest you can to it. Nice. Any other one from any of these homeworks? These are really important homeworks. I hope you guys did okay on them. I see a lot of people missed number 3 and a lot of people missed number 1 and number 3 and number 8 also. Should we go over, do you guys want to see number 3? Okay, let's take a look at number 3. Maybe you guys can try it again, those of you who missed it. So the distribution of durations for which apartments remain empty is approximately normal. Okay, so we can use the bell curve with mean 85 and standard deviation 29 days. They want to tag the files of apartments that were really like not empty for a very long time so that they can clean them out faster. But those are like urgent apartments. What is the maximum duration for which an apartment would need to remain empty for the company to tag its file? So how about you guys, if you missed this exercise, just try it out for like 2 or 3 minutes. Go to ztable.com and see if you can solve it. I mean, the answer is up here, but you know, try it out and let me know if you have any difficulty solving it. Just making sure that everybody in class feels really confident in doing these. And there's really not much to them once you get the hang of it. So I'll wait for like 2 or 3 minutes and then you guys just message me when you're done. Let me know if you need some help or if you're a little bit stuck.
Does it show? So like it says, I see on the side, it will tell you how many people got it right, how many people got it wrong.
Mm-hmm.
If you retake it, will it correct it or no?
You know what? Actually, hang on. Wait a second. This is a lot of 24 people. I'm confused here. What? I'm confused what does this mean? Responses, draw. Oh, that's cool. I can do this. But I'm not sure actually what this means. Okay. So 14 students got this right, but it says only 10 students got it right here. Maybe it's like on your first try?
Yeah, for me, a lot of them I got wrong on my first try, and then I was like, after I understood it, I started getting them, I went back and got them right.
Oh, nice. Okay, cool.
I think that's what a lot of people did.
Okay, cool. Okay, actually, this one looks like, this one actually, I misread it. I thought the X was, I thought the bigger bar was the one students got correct because I know they let you retry them. So maybe we'll discuss this one also after. But it's the same thing. Okay, how did you guys do? Any questions? Angel, you want to walk us through what you did?
So the Z-score of 0.05, the one that we are given, is closest to the Z-score of 0.0495, or the probability of Z being less than 1.65. So substituting that in the equation of X of Z being equals to X minus the average over the standard deviation, it gives the answer of around 37.
Nice. And remember, because it's negative, so very good, Angel. Do you see that the key here is you want to use the negative Z-score because it's 5%. It's at the bottom of the Z-score chart curve. So the Z-score that you should have is negative 1.6. And when I see negative 1.6 as a Z-score, I'm thinking, okay, we're almost about a 1.5 standard deviations below average. So you do, what you would do here is you do 85, but then take away 1.65 times 29. So this way you would be below average. If you made an error, did you find where you went wrong? Or are there any questions on this one? Yeah. Oh, any questions at all? And let's see, number 2. So this one is, okay, so maybe this one's just slightly different here. I saw somebody, I think Brandon mentioned it, or somebody else mentioned it, I forgot. What do we have to be careful when we're looking up this one? The distribution of scores at the school is a normal distribution with mean 221 and standard deviation 36. But this time we want to find the top 20%. So if we want to find the top 20%, what probability do we want to look up in the z-score table? Nice, Angel. Nice, Colette, very good. So we look up 0.8 because that would give us the corresponding z-score. You could also look up 20%, but then you just have to remember that you don't want to subtract that number. You want to actually add that number to the mean. Okay. Any questions at all? Like anything you want to see in more detail? I'm happy to go over either the last one in more detail or this one. Or do you feel comfortable to move on? Did this help a little bit? And don't. Yeah, let's try it. Okay, let's do number 2 together. Yeah, let's do it. Let me. So I'm just going to write it down. I'm going to share my screen now. Awesome. I got a few people. Yeah, let's just do it really quick. But I'm glad that a few students feel pretty comfortable with it. That's awesome. All right. So this is just number 2. So for number 2, in that same section, we know that mu is equal to 221 and sigma is equal to 36. We want to find the top 20%. Find the test score for the top 20%. So I'm going to go to ztable.com. So look up, for the z-score that gives probability that x is greater than z is greater than 0.8. That would mean that I'm in the top 20%. So I'm looking for this z value. X is just a dummy variable. So I look up 0.8 in the table. 0.8, the closest thing I can find to 0.8 is 0.8023. So, this is a really unfortunate number because it's very close. So probability of 0.8023 corresponds to z-score of what is it here? 0.85. So be very careful when you're writing about these things. Sometimes these numbers are kind of confusing. Like this is a probability, but this is not a probability. This is a z-score. This tells you how many standard deviations away you are from the mean. So even though the numbers are close, they're not the same. So definitely don't mix those up. And now that we know the z-score and we have these quantities, we can figure out the x value or the threshold value. So we want to say x is equal to 221 plus 36 times 0.85. And if you do that in the calculator, yeah, so Archer, yeah, I agree. You can use 0.84 as well. Although it said, so the thing that you have to be careful with is if it said that it needs to be the top 20%. So if you pick 0.84, that actually gets you just a little bit below 20%. I mean, it's a tiny, tiny amount. Either one is fine, but I was just kind of being extra careful so that the score would guarantee that. But you know, at the end of the day, this sort of analysis or this approach is using an assumption that anyhow, the assumption is that the bell curve fits the distribution pretty well. If you have a distribution of test scores, it's not going to be a continuous distribution, right? Because there's not an infinite number of people. Let's see here. 221 plus 36 times 0.85. Or you could definitely use 0.84 instead if you want. So I got 251.6. So if you're over that score, you're going to be in the top 20%. Okay, any questions on any of these? Thumbs up if you feel better or feel pretty comfortable. And okay, any other homework that you guys wanted to review from this last? I didn't actually assign the Khan Academy stuff. I'll try to do that today, but I posted the section so you can start working on that. But I'll assign them today as well. Okay, let's get started with the lesson. So last time we saw that I'm going to write it like this. So I'm just going to restate it. So we saw that this is the central limit theorem. So we saw the following: the distribution of a sample mean where the sample consists of IID random variables. So this IID is something you read about a lot in statistics and probability. It stands for independent and identically distributed random variables. So the way I think of this again, if something is an IID variable, it's like you have the same dice roll and you're just rolling it over and over, or you give like 1,000 people the same dice roll or same dice, and they just roll it one time and you record all the results. So each dice roll is identically distributed and independent of the other. And each dice or each distribution random variable that you work with has mean mu and standard deviation sigma. So the distribution of a sample mean, where each sample consists of an IID random variable with mean sigma and standard deviation I'm sorry, mean mu and standard deviation sigma, the distribution of the sample mean. So this thing this will, maybe I'll put a comma. So that the distribution of that sample mean will approach a normal distribution, a normal bell curve with mean mu, and the standard deviation is sigma divided by root n, where n is the sample size. So another way of writing this that we use is x bar is distributed. This symbol means distributed, like, so this is the this is how it's distributed. It has the same distribution as a normal bell curve with mean, well, this is just the definition of any, of a bell curve, mu x bar, sigma x bar. These are the mean and the standard deviation of x bar, the sampling distribution. And this is the same thing as the normal distribution, but with mean mu x and standard deviation sigma. I'm just going to do actually mean. I don't think it means sigma over root n. And you can write something also similar for the distribution of a sample sum. So the distribution, and we actually kind of already saw it, of a sample sum. Let's call it y is equal to the sum of xi, y equals 1 to n. So what do you guys think is the difference between the sample sum, where the sample sum, we just, rather than, the sample sum just means do the, collect all your data and just add up all the outcomes. What's the only difference between the sample sum and the sample average? Does anyone know? What's the only difference between the sample sum and the sample average? How do you get from one to the other? What do you guys think? Does anyone see how you might relate a sample sum and a sample mean? There's a really simple relation between them. Everybody knows it, actually. If I roll 100 dice and I add them all up, that's called the sample sum. How does that relate to the sample mean of that experiment? So sample mean, to get the sample mean, right, you just have to add up all of your outcomes and divide by the sample size, n. That's the sample mean. The sample sum is essentially the same thing as the sample mean, except you just add them all up, but you don't divide. So we can express it in a nice way. We can actually write it as equal to n times the sample mean. This is a really simple equation, right? If you divide both sides by n, you get the sample mean. Let me put the bar here. So the sample mean, which I'm just going to write sum xi. This is going to be distributed. Well, whenever you multiply a distribution times a constant, the expected value also gets multiplied by that constant. Like, for example, do you guys see that if you roll 100 dice, right, what would you expect the total to be close to? If you rolled 100 dice, not the average roll, but what would you expect the total to be close to? You rolled 100 dice. Any thoughts? Well, remember each dice we expect to be, it has an expected value of 3.5. So if we roll 100 of them, and we add them all together, we'd expect to be pretty close to 350. So it tells us that the sample sum is approximately normal with distribution n times mu. And the standard deviation, the variance gets multiplied by n squared. Therefore, if we take the square root, the variance gets multiplied just by n, but the variance of the sample mean. So if you multiply this by n, you get square root n times sigma. And so this, if you roll 100 dice, we saw that the sample mean was around, the sample standard deviation was around like 2 something, I believe. So if you roll 100 dice, you maybe expect most of the total to be between like, somewhere between maybe like 200 and 500, something like that. Okay. Oh, sorry, not 200, 500. You multiply by times the square root of n. So it'll be around plus or minus 20 or so. So you'd expect to be somewhere between 330 and 370, which makes sense. So the idea is that the spread is getting larger, but it's getting relative to the overall kind of possibility of outcomes ranging from 0 to all the way to 600, the actual interval where you expect most of these sums to fall is actually pretty narrow relative to the entire range of outcomes when you're just considering the sum. So these are very, very much related. The sum and the sample mean. They're just related by a factor of n. All right, let's try some examples. So you guys try these out and let me know if you need some help. Are there any questions on what I just talked about? Okay, so let's try an example here. So giraffe heights are normally distributed with mu, they're about 15 feet tall, and standard deviation is equal to 7.5 feet. If you take a random sample, of 25 giraffes, what is the probability that the average of your sample is less than 15.5? All right, so guys, please try this out on your own, because now you have all the tools to do this. And I'll give you guys maybe like 4 or 5 minutes to work on this. Let me know if you're totally stuck, you just don't know where to start. And after we do this example, we'll do one that's about the sum. And you'll see kind of cases when you want, this is about the average, because you want to see what's the chance that the sample average of your 25 giraffes is less than 15.5. And in the next example, we'll see a situation where you want to use the sum, but they're pretty much equivalent. There's not much of a difference between them. Okay, so first idea is that X bar, right? What kind of distribution does X bar follow? That's the first question. What kind of shape does it follow? Just the overall sample mean. The sample mean, according to the central limit theorem, has a bell curve shape. Now, what do we know about the bell curve here? The bell curve shape of the sample mean, what is the middle of the bell curve shape going to be? So first we need to identify what's the bell curve shape that the sample mean follows. The middle will be 15.5. Oh, no, sorry, not 15.5. The middle will be the middle of a regular giraffe. Like this is the, if you take a single giraffe, you expect, to see on average about 15 feet, plus or minus 7.5 feet. So there's quite a big range for picking a single giraffe. Like if you saw a giraffe that was 7 feet, you wouldn't be too weirded out. And if you saw a giraffe that was like 22 feet, that could happen. So that's a single giraffe. And so the average, if you take 25 giraffes and take their average, you would also expect the middle to be the expected value of the sample mean to also be 15. Okay, so the next part is, how about the distribution, the standard deviation of the sample mean? So if you just picked one giraffe, plus or minus 7.5 feet could definitely happen. That's the idea there. It's one standard deviation. But what is the standard deviation of the sample mean? What would that be? Almost. So 7.5 is the standard deviation of the single giraffe. But as you take more giraffes, right? As you take 25 giraffes, you get a number and you take their average. That's also a random number and it's got some distribution. And it's going to have less variation because you're taking 25 of them and you're averaging them. So in that case, you have to use this formula. You have to find sigma, the original sigma. This is sigma of the sample mean. And this formula tells us that this the standard deviation of the sampling distribution is the original standard deviation, which was 7.5, but you got to divide it by the square root of 25. So I'm going to write it over here. So this tells us that x bar is distributed like a bell curve with mean 15. And usually the first number is the mean. And standard deviation is going to be 7.5 divided by 5. And so this is just going to be a normal bell curve with mean 15 and standard deviation. 75 divided by 5 is 1.5. So any questions on how I got to this? It's really one step. And this is the key, right? Now that you have this bell curve, whenever you know the mean and the standard deviation of a bell curve, you can answer any kind of question like this. And we don't even care. X bar is just a symbol, right? If this was a U, I could do it with U. If this was a W or a V or who knows, as long as this symbol is the same as this, right? It's just telling me about the distribution. Okay, so now we got to find the z-score corresponding to this value. So, and I like to draw a picture here. I'll draw a picture roughly around here. So here's 15 is the middle. Here's 15.5. This is kind of what I want, 15.5. But I know that most of the data is roughly like 1.5 away. So I don't have to fully draw that. This is sigma. I can write a sigma equals 1.5. We're going to find the probability of this region. Okay. So I got to use the z-table. I got to find the z-score. So z is how many standard deviations away am I? Well, it's 15.5 x minus mu. So 15.5 minus 15 divided by 1.5. This is exactly 1/3. So it's going to be 0.33 repeat. You definitely need to do the square root. Yeah. Divided by the square root of 20. So now I go to the ztable.com and I look up the z value of 0.5, because remember now I'm going from a threshold value, a certain range of the height, a certain like measure of height, and I want to actually, I'm trying to get a probability. So if I look up 0.33 on the table, is equal to 0.33, I got 0.6293. So I'm going to write it really carefully. Probability, and this is what I'm going to look for when you're doing the test. So probability that x bar is less than 15.5, after you do the z-score, you're basically just standardizing it. So we write this is equal to the probability that the z-score is less than 0.33. And if you look at the table, that looks like about 0.6293, which is 62, about roughly 63%. Nice, Archer, very good. So there's a 63% chance that you find a draft that's going to be less than 15.5. And at first glance, that might not seem really interesting, right? But it's a, this idea of the sample distribution is very powerful, because 15.5 is actually really, really close to 15. So if you just pick one giraffe, you'd probably expect like the chance that you observe something below 15.5, it should probably be around 50%, because 15.5 is super close to 15. But because now you're doing a sample of 25 giraffes, you're much more likely to observe something less than 15.5. And that's really close to 15. So and that's not super surprising. As you take a larger sample, you expect that there's less variation in your random average that you're going to compute. Any questions on this example? How many of you got it and felt really comfortable with all of the steps? Just, oh, how do I find the z-score? Okay, so, this one. Lily, are you referring to this part? How did I do this calculation? Oh, on the table. Okay. So I have the z-score. This is the z-score, 0.33. Is that okay? How we got that? That's just the number of standard deviations that you're looking for using this number 1.5. So this is 0.333. Now I go to the table. Let me just share my screen. And I look up 0.33, as 3 is the 100th and the 10th place. So this is the 10th place, and this is the 100th place of your z value. So these are not probabilities. This is just the number of standard deviations. So look at 0.33, and I just got this number. This is now every number inside of the table is a probability. So this is the area under the curve. It's telling me that about 63% of the area is to the left of 0.33 in the standard normal. Good question. Watson asks, where did the 1.5 come from again? That's a really, really important question. Anyone want to take a stab at that one? How did we get 1.5? Any volunteer to answer that? Brendan, go ahead.
You divide 7.5 by 5 and you get 1.5.
Nice. Why divide by 5? Where did that come from?
Because since we're sampling from 25 giraffes, we just square root 25 to get 5. And then after we square root that, then we can just divide the standard deviation or sigma by 7.5.
Awesome. Let me just share. Sorry, I wasn't sharing the whiteboard there. Thank you, Brendan. That was great. So the standard deviation of the sample mean is similar to the standard deviation of a single giraffe, but you have to make sure you divide by the square root of your sample size. Exactly. And so that's what makes the standard deviation of the sample mean a little bit narrower, and it makes it less, you have less variation. When you take the mean, you're not expecting to see like a really wide range of values when you're taking the average of 25 things. And the more things you take the average of, the less variation you expect to see in that average. Any questions? Awesome, really good. How do you guys feel? What do you think? Cool. Use some more practice. Okay, cool. There will be more practice. I will post the homework. You get a bunch more practice on this, and hopefully hopefully it clicks as you're doing this that it's essentially the same problem over and over. You just have to know what to use for mu and what to use for sigma. And I really want you guys to focus on writing everything properly. So I see sometimes people write this. Do not do this. So don't do this. Don't do things like this. Z, like this is if you're rushing and being sloppy. I've seen a lot of students who do this. Z equals 0.33, which equals 0.6293. So do you guys see why I don't like that? It's, you kind of did, you did all the right steps and you kind of know what to do, but do you guys agree that that looks really bad? It just doesn't mean anything, right? Like 0.33 does not equal to 0.6293 as a probability. But if you say, if you write this notation, probability that the z-score is less than 0.33, this probability is 0.6293. Now we're talking. That makes sense. You could also write, if you wanted to, if you don't, like I personally like this. This is kind of the way that is customary. But if you want to use an arrow, you could also do, you could write it like this. So z-score, z equals 0.33. This gives a probability of 63% to the left. You could write something like that if you wanted to, like an arrow. But just, Archer, yes, this question asks about probability. Oh, with the Archer, what do you mean by your question? Write the answer, like on a test? Okay, cool. Yeah, on a test, I would like to see something like this. This is what I would look. And just writing everything properly. And don't do this. Okay, let's do the next question. So you guys can see what I mean by summation. Why would we be interested in not the sample mean, but the sum of several random variables? And by the way, this is actually something you might notice if you ever take an elevator. An elevator has a load capacity of 1,000 pounds. Assume that human weight distribution has a mean of 160 pounds and a standard deviation of 20 pounds. So here's an interesting question. If 6 people entered the elevator, what is the probability that it would be overweight? Over capacity. Okay, so what do you guys think would be a good random variable to introduce here? So we have 6 people, each of them has a random weight, but what are we really interested in measuring? Any volunteers? Any ideas? Their total weight, right? So let's write that. Nice, Angel, very good. So we can write W as their total weight. It's a random variable, and it's the sum, if you remember this notation, from the first person to the sixth person, just adding up all their weights, where xi is each weight. So here's a kind of intuitive question to ask. What is the expected value of capital W? If you take 6 people, each person has, you expect each person to roughly be 160 pounds. What would be the expected value of capital W, which is 6 people? What do you guys think? So each person's expected weight, a person's expected weight is 160 pounds. Nice, exactly. Yeah, 6 times the average, 960. Very good. So that's pretty intuitive. So you do 6 times mu, which was the original 160, and you just get 6 times 160 is going to be 960 pounds. So, okay, that's pretty close to 1,000 pounds. So now we're saying, hey, there's 6 people here. The elevator only holds 1,000 pounds. We're going to, 960 seems pretty close. But what about the standard deviation? Because in order to understand how, is 1,000 actually close to 960, is it likely to happen? We need to know how this W, what's the standard deviation for? So that's where sigma W comes in. And if you recall, the formula for sigma W is square root of n times the original sigma of a single person. And so in this case, it's going to be square root of 6 times 20, which is, just put it in my calculator here or Google, square root SQRT of 6 times 20. I got 48.9. So let's just, let's see if we can use that, 48.9. Okay. So similar to how for sample mean, you take the standard deviation and you divide it by square root of n, for the sample sum, you take the standard deviation and you multiply by the square root of n. Because you're no longer, when you take the average, you make everything, you make your sample, you overall divide it by n. But here we're no longer dividing by n. So that's why we have the square root of n up in. And this is, again, related to what we talked about last time about how the variance works. Okay. So any questions on how I got the average value for W and the standard deviation of W? Or was it 48.8? I got 48.98. Oh, I almost got, but I did it on Google here. I don't know. It's not a big, very close. I almost got 49, like 48.98. Did anyone get something different? Brent, how did you do it? I'm curious what you did. Maybe my calculation's off too. I don't know. Oh, okay, cool. So you rounded the square root. I think that might just be why. But that's totally fine. Yeah, it doesn't have to be perfectly. It could be within the 10th. All right. So now we know that. Now let's answer the question. So we no longer need to worry about sample sum or anything like that. We can just use these numbers and find z-scores. So we have this number and this number as our standard deviation. And we want to find what's the probability that it's over 1,000. So I'm going to write it over carefully. What's the probability that W is greater than 1,000? That's what we want to answer. Well, this is equal to, so let's find the z-score. The z-score is equal to 1,000 we want to see how far away am I from the standard, from the mean. Over 960, so about 40 units away. But how many standard deviations is it? So over 48.9. So this will be 40 over 48 point, it's basically 48.98 actually. It's really close. And so let's just see what that's going to be. So 40 divided by 48.98. This is about 0.81. 0.81, yeah, that's all we need, right? We only need to the hundredths. So the probability that this is equal to the probability that the z value is greater than 0.81. Well, bell curves, remember, don't tell me to the area to greater than, so I have to adjust that. So if I do something like this, I'm just going to draw out my z curve. This is z distribution. Here's 0.81, and I want to know the chance that it's greater than 0.81, so that's over here. So instead I can do 1 minus, oops, 1 minus the probability that z is less than 0.81. And now I'm going to go to the z-score table, and then we're going to look up 0.81 as a z-score, and that is going to be 0.81 is 0.7910. 0.790. So subtracting those, 1 minus 0.791 is 0.209. So this is about a roughly a 20.9% chance that we're over capacity. So not entirely insignificant. Lily, yes, good question. So whenever we want to find the area greater than a certain z-score, we do it because the table only gives us the area to the left. So we do 1 minus the area to the left whenever we want to do something greater. Angel makes Angel, do you want to share your comment? There's another way to do it, which is really nice as well. Actually, Angel, be careful. You don't want to do 0.19. You want to look up negative 0.81. Because remember, this is not a probability. This is a z-score. So if there's a shortcut, if you don't want to do the subtraction, you can look up the negative z-score of 0.81, which would be negative 0.81, and find the area to the left. Because remember, bell curves are symmetric. So if instead you wanted to find the area using a sneakier way, you could just look up negative 0.81 right away in the table, and that would give you 20.9% as well. Angel, did you catch a mistake there? Cool. That's a really good mistake. And Lily, do you see the other way of doing it as well? I personally just like to do 1 minus so I don't get confused, but either way is good. Okay, so that's how we might be interested in understanding the distribution of a sum. I'm just going to leave you guys with one last concept here. And this is actually so last concept here, then I'll let you guys go. And you can get more practice, you'll get more practice on these for the homework. So this is the distribution of something called the sample proportion. So, so here's it's called the So assume that 70% of the US answers yes to the question, so yes or no question. The question is your pizza your favorite food? And it's a yes or no question. It's not like what's your favorite food or list your top 3 favorite foods. It just said, is pizza your favorite food? And so what we can do is we can create a random variable that's based on this information. And the way we do it is anytime there's a yes or no question, you can count the number of people that say yes by anytime somebody says yes, you give them a 1. And if they say no, you give them a 0. So we can create a random variable for a single person, xi, kind of like a dice roll, but instead of having numbers 1 through 6, it just has numbers 1 and 0. Or it's kind of like a coin flip, right? Yes for like heads could be yes, tails could be no. But instead of heads and tails, we do 1 and 0 because we want to count the number of yeses, or we want to understand something about the number of yeses. So this is x sub I is 1 if yes and 0 if no. So let's actually write out this random variable. Let's do the chart. And let's do it together. So if you recall, for a random variable, we put x, we make a little table for the outcomes and the chance of each outcome. So in this case, what is the chance of observing, if you go to a person, what's the chance that they say no? What's the chance of observing a 0? If you ask them, is pizza your favorite food? What would be the chance of getting a 0?
30%.
30%, so this is 0.3. And sometimes we write it as, we'll call this, for these types of probabilities that are kind of 1 and 0, there's a special name for them, they're called Bernoulli variables. We write P is the probability of success, and Q is the probability of failure or no. And with the probability of success, therefore, of somebody saying yes is 70%, which we call P. So there's really, P determines everything. So there's a 70% chance of getting a 1 and a 1 minus P chance of getting a 0. In this case, the specific numbers are 70 and 3. Okay, so here's where it gets interesting. How do we find the expected value? What do you guys think? What is the expected value? If you went to 100 people, right, and you said, you counted how many people say 1, how many people say 0, and you take the average of that, what would you expect to get? What is the expected value of single x? And you can also use the table here. Does anyone see what it is? It's a really simple calculation because this table is really simple. What would the expected value be? Not 1. 1 is what you get if somebody says yes. But do you always expect to get a 1? You have to account for the fact that sometimes people give you a 0. Remember how we used the table, the x and p of x table, to get the expected value? Yeah, Colette, how did you get 0.7?
Well, I just got 0.7 because that's literally like there are 0.7 or 70% of the US answers yes to the question. So it was more of like just like a logic thing, but I know that there's also an equation you can use.
Yeah, so good job. That's the intuition that you expect. The expected value, if you just come up to a random person, you expect their score to be 0.7, which is nice because if you went to 100 people, you'd expect about 70 of them to say yes. That's the interpretation there. But remember the idea for calculating expected value, you just take this number, the outcome, times the probability, and then you do the same thing for each outcome. So I'm going to do it with a formula. I'm going to do 0 times 1 minus p. Okay, that's just going to be 0 plus 1 times p. So this just becomes p. In this case, it's 0.7. But in general, exactly, very good. In general, it's just going to be the probability that you originally assigned, which makes sense. Okay, now it's interesting, and this is going to get us to a formula. What about the variance? So if you recall, the variance of x, the variance is the expected value of not x, but the each outcome minus the expected value squared. So let's do it up here. So x minus mu squared. So this is going to be 0 minus 0.7 squared. And this is 1 minus 0.7 squared. But let's do it as a formula. So, because mu is really simple. Mu is just p. So I'm going to do it as a formula. So what I'm going to do is I'm going to first calculate this thing. Instead of 0.7, I'm just going to replace it with p. So I'm going to write 0 minus p squared times 1 minus p. That's this number times this one. Plus 1 minus p squared times p. Do you guys follow those steps? Oh, is that how? I didn't actually 0.49. So this is just the steps of, like, for a Bernoulli variable, finding the variance. And now we're going to see something really neat that happens here when we do this calculation. Do you guys see that there's a factor of 1 minus p over here and over here that we can just take it out? So I'm just going to do a little bit of algebra, and I encourage you to try this out on your home if you're a little bit confused here, because it's how you get a useful formula. So you take out 1 minus p, and what's left in the parentheses, negative p squared just is the same as p squared, plus 1 minus p times p. And this, just to go to a new page, this becomes 1 minus p. And can anyone tell me what happens to the expression in the brackets? Do you guys see? What happens when you do p squared plus, in parentheses, 1 minus p times p? Take a look at what happens here. They cancel, and all you're left with, the p squared here, this is a negative, this is p minus p squared. So p squared, it cancels with negative p squared, leaving you with a really simple, just a p here. So the variance is 1 minus p times p, or sometimes you see it in books as p times q.
Wouldn't the 0 minus p though become a negative p square? Oh wait, it's squared. Never mind.
Well, oh yeah. Good. It's that's squared. So just a little bit of algebra there, but we find that the variance of x is p cubed. Okay. So now we can answer our question that the variance of our case was for the pizza question. I'm going to write still xi was 0.7 times 0.3. And so the standard deviation was the square root of 0.7 times 0.3, which is the square root of 0.7 times 0.3 is roughly 0.45. So this is for a single person. If you have a single person, you'd expect them to say, the score you would expect is about 0.7. Of course, if people only give you a 0 or 1, that nobody's ever going to tell you 0.7. But the interpretation is that if you ask 100 people, you'd expect about 70 of them to reply that, yes, pizza is my favorite food. And for the distribution, you find that the standard deviation is about 0.45. And so we can use this information in the following way. So, and this is the last thing I'll let you guys go. Assuming the above, and take a moment to review what we talked about here so that you see the ties to what we did earlier. So assuming the above, if you were to ask ask 100 people, is pizza your favorite food? What is the probability that the sample proportion, so the percentage of the people that you ask, that's the sample proportion. And we have a letter for that. We have a special symbol we use. We say P. This is confusing because it's not a probability, it's a proportion. What's the probability that the sample proportion P hat is less than 0.75 or 75%. So what do? How do we answer that? Well, what is P hat? P hat is essentially the way to calculate the sample proportion is you add together what everybody said, 1 or 0. So you count how many people say that they like pizza, equals 1 to 100. And then you divide out of how many people there are. Does anyone recognize what this formula really is? Sample proportion? What is it really in disguise? If you add 100 random variables and then you divide by 100, it's just a sample mean of these types of random variables. A special one is just 0 or 1. So sample proportion is really just a special sample mean in disguise. So this is just sample mean in disguise. So it looks like a different type of problem, a different type of formula, but it's really the same thing. So it's a really problem that you already know how to solve. So that tells us that the mean of P hat is equal to just the original mean of X. So we'd expect if we asked 100 people we calculated the proportion that say yes, we'd better expect that 70% will say yes. So that's the mean of P hat. And the standard deviation of P hat is kind of interesting. The standard deviation of the sample proportion, well, we know how to do that. We take the standard deviation of a single person saying yes or no, and we divide it by the square root of n. So in this case, I'll write down the formula. We know that the standard deviation of a single response is square root of PQ, and then you divide it by the square root of n, it becomes square root of PQ over n. And remember, this is just because of the way sample mean works, and that p hat is secretly a sample mean. And so you can actually calculate this now. Would be 0.45 over, this would be, was it 0.45 divided by square root of 100, which was 0.045. So now we know that p hat by the central limit theorem is about kind of like a normal bell curve, but with mean 0.7 and standard deviation about 5%, 0.045. So we can find the chance that we get something less than 75%. It's actually going to be pretty likely, probably 80% or so, something like that. So I'll leave that for you guys to do, but I'll just put this kind of a final analogy here. There's a connection between mu is the same as p when you're talking about the Bernoulli variable. I'll write down that name. So this is for Bernoulli variable. So Bernoulli, he was a mathematician. They were actually brothers, and they studied probability, and they came up with the random variable that gives either, it's good for like yes or no type of experiments. That gives 0 or 1. And X bar is completely analogous to p hat, the sample proportion. So you can answer this question now just using the table. All right, guys, I'll stop there. Please try out the homework, some of the homework before Thursday, and we can continue. On Thursday, I want to continue with confidence intervals. And then next week, we'll do a little bit about hypothesis testing and t-tests. And I think we'll have like maybe 3 more lectures and then focus on getting you guys ready for the final, which will be the last week of May. I think towards the end of May. So about, today's the 11th. So maybe like around 2.5, 3 weeks or so. So, but 3 more lessons of content, and we can also practice, do more practice. All right, any questions?
Have a great rest of your day. See you Thursday.
Okay. All right, guys, see you Thursday. Bye.
Thank you.
Thank you. I'll be around if you guys have.
Thank you.
Bye.
Hi, Mr. Minsky. I'm ready to take my retake now.
Okay, great. Let me send it to you. All right, Donnie, I think I sent it to you. Let me know if you got it.
All right, let me see. Yeah, I got it.
Awesome.